Hi, this is Steve Hambric of the Center for Acoustics and Vibration at Penn State University, and I'm here to give you an overview of the Structural Vibration and Acoustics group. We have many members, as you can see here, along with a lot of students, and I'm going to give you an overview of the group and highlight some of the more exciting new student research we've got going on. Pleased to announce we've got new faculty members, so welcome to Cez, Nathan, and Daneng. And if you go to the Penn State newsletter for the recent year, you can find short profiles on each of these fine new additions to the group. I'd like to highlight mainly student work here, and in particular, there's some posters that you'll see available in the poster session on Tuesday. And here they are from our particular group. There's a total of 23 total competitors. And here are some of the folks from our group, starting off with some drivetrain modeling and spur gear work that Sean Gaunt is doing, advised by Dr. Rob Campbell. Connor McCluskey is looking at a lot of extreme value and uncertainty work, in particular looking at the variances that you might see in flow-induced load prediction. And Matt Gers and Steve Conlon are advising Connor. Some of you that attended last year may remember a demo that we did courtesy of our friends up at Gauss at Sherbrooke, where they did some real-time optical deflectometry measurements of plate vibration. And we're happy that Gary Rhodes has continued on looking at that work with Micah Shepard and with help from Olivier Robin of Sherbrooke. John Young is looking at power flow between structures, and Kyle Myers and Rob Campbell are advising John. And finally, one of our new members, Nathan Brown, is advising John Broyles, looking at structural acoustics of concrete floors. So check all of their posters out tomorrow and learn more about what they're up to. There's a lot of other work going on, and this is not all of it, but here's some new highlights. I've got Tom Blanford and Trevor Jerome, who just graduated, that are working with Micah Shepard on scaling the vibroacoustic behavior of cellos. So that was kind of fun work. That was a bit of a spin-off on some work that Micah did for Martin Guitar. And you can see that work highlighted in our newsletter as well. We're using more and more high-speed digital cameras and a method called digital image correlation, DIC, to try to help us with some of our vibration measurements. And Sean Collier has been looking into that along with Dr. Tyler Dare. We also find ourselves working more and more on vibrations and fatigue life. And so here we've got a student that Matt Gers is advising go to say on fatigue damage and how you in particular can accelerate your testing. The last two are on a really fun topic that we did a short course on last year, acoustic black holes. And Yu Xiong has been working on embedded acoustic black holes inside structures, and in particular, how to reduce vibration and radiated sound. And Cam McCormick is real close to graduating, and he's looking at optimizing the black hole shapes and treatments. And I'll highlight some of that work a little bit at the very end here today. Always pleased to announce when our students graduate. Trevor, as I mentioned, just finished up. He was actually not working on cellos, but bolted joint dynamics. So I'll give you a highlight of some of his work. And Micah and I both advised Trevor. And Steve Wells just finished up a big project looking at chiller noise, in particular, very large chiller noise and vibration that was sponsored by Carrier. And my colleague Tim Brungart and I advised Steve. And then finally, Gage Walters just finished some exciting work on uncertainty quantification and predictions, and hard predictions too, flow-induced vibration and sound predictions. And Andy Wixom and Sherry Martinelli advised Gage. And so in fact, these are the three that I'm going to be spending a fair bit of time on through the rest of this presentation. So let's jump into what Trevor did. And we're pleased that the NAVC Warfare Center sponsored Trevor's work, and also that he went to work at Carderock when he was done. So it's a big win for them. They sponsor the work, and they also got to keep Trevor around to help them with vibration work going forward. So bolted joints have always been difficult to model. We're still not there yet, but Trevor got us a fair ways further. And it's just so hard. You might think that a bolted joint is just almost rigidly connected, but it's not even close to the truth. And if you go back in time, there have been some empirical techniques for estimating what the bolted joint region looks like. So in the example we've got here, we've got a bolt up at the top, maybe a nut at the bottom, and then two structures bolted together. And there are these kind of frustum models that people have proposed that say, okay, if you look at the size of the connected structure and the bolt and all of that, you can project down at an assumed angle. Early models suggested 45 degrees. Others have gone between 30 and 60. It's really a mystery. It just depends on the structure. And you kind of say that, okay, this is the region that's clamped tightly together. And in fact, outside of that region, you're not so tightly clamped. And in fact, if you look at a nonlinear static finite element model solution of a bolted joint like we have here, you can see what happens as you crank down on the bolt and you bolt these, or you preload these bolts quite a bit, typically up to about maybe 2/3 of the yield strength or yield stress of the bolt material itself. And this is highly exaggerated, but it shows what happens. You do wind up with a fairly well-connected region just around the bolt, which looks like it's got a frustum kind of shape to it. But look what happens away from the bolt. The material actually pulls apart. So you're compressing here, but you're pulling apart outside here. And if there's an adjacent bolt a certain ways down, which is quite typical, then that would clamp down and you would have this kind of open region around it. So you wind up with all these sort of localized connected regions and then open regions elsewhere, which was frankly a surprise to me when we first started looking into this. So what Trevor wanted to do was go through and predict this sort of behavior and also measure it. So he did a bunch of measurements, starting with just looking at the contact pressure region. What does that contact region look like? And he did those measurements using an ultrasonic probe. And so here are a couple of plates with a bunch of holes in them, and you can kind of see where we did most of the bolting. These actual holes are in fact for pins to make sure that the structure didn't move as we were doing the testing. And we had a kind of a control opening here where we didn't have a bolt, and then the bolt over here on the right, because when you use ultrasonics, you never get a perfect measurement. The whole idea here is to take a probe, and now we're looking at the plates bolted together along the side, and then run the probe along the surface and get a 2D scan of what the pressure, contact pressure looks like over this entire region. And what you find is that you get a highly localized contact region around the bolt and then very little contact elsewhere. And the way you can tell that is by looking at the reflections that come off of the surface. And if you get a strong reflection, that means you do not have a whole lot of contact. If you get a weak reflection, that means that the ultrasonic wave goes all the way through to the bottom of the total bolted assembly and comes back up the other side. And so what you're looking for is essentially the reflection from the interface. So you can tie the strength of that reflection to how tightly bonded that surface is. And when you do these scans over the whole surface and then do some manipulation with the ultrasonic reflection coefficients, you can get these nice contours of what that region looks like. So on the left is what you get when you have no bolt at all. And so the reason we include this is it's an ultrasonic probe. The waves disperse a little bit when they're sent in. And so you don't get this perfect reflection. You wind up with kind of a smeared reflection. So when you look here where there's no bolt at all, you wind up with something that looks like you got something along that bolt, but you really haven't. So we want to compare that to what's happening along the bolted region. So here you wind up with very little reflection along certain regions, very high reflections in others, and you get a highly localized contact region here. And you can convert that to an actual pressure. And once you have the pressure, you can further convert that to something called an interfacial stiffness, essentially what that localized spring constant looks like around the contact region. And so the way Trevor's plotting this is we start at the origin, the center of the bolt hole, and then move out to the edge, and then continue on beyond that up to about 3 radii. The black is essentially your noise floor. That's what you get without a bolt at all. It'd be over here to the left. So this isn't real. This is just an artifact of the ultrasonic measurements. But over on the right, the colored dots are what you get around the bolted region. And you get a much higher stiffness as you get closer and closer to the center line. That's where the pressure is highest. And as you move further and further away, the pressure and the corresponding stiffness go down even more. You're seeing a bunch of dots because we're looking at different cuts around the circumference, a full 360-degree sweep around. And so, for example, the light blue dots happen to correspond to right around here. You can see them all through here. Red dots over here. And so there's some variability, and you can see in the contour as well. It's not a perfect circle. And that's because nothing is perfect, right? You bolt this on, and you've got the threads that are helical. The surface roughness is not perfectly uniform. The measurement itself is not perfect, and so there's always a little bit of variation here. But this is a pretty clean measurement. And then the red line is an average over all of that. So you wind up with a pretty strong stiffness out to about maybe a 1.5 radii, and maybe some stiffness beyond that. And then by the time you get up to 3 radii, you pretty much don't have any strong connection at all anymore. So the next set of tests he did, and we're actually showing you simulations here because they're easier to visualize, is of 2 bolted plates. And so we built 2 of these guys with different lengths and different flanges. So this is in fact 2 different flanges bolted together at 2 locations. And we did a bunch of, Trevor did a bunch of modal tests on these plates and pulled out the resonance frequencies, but also pulled out the damping. And I'll show you in a minute that he looked at what happens to the frequencies as well as the damping when you vary how strongly you excite these structures. And as we looked at the results, it became pretty clear that we had 2 types of modes and 2 types of behavior at the joint. And so this first type of behavior is just a bending motion. And if you zoom in on the flange, I've got a bolt here, we're just showing one of the bolts. As the plate vibrates, you wind up with this sort of slapping region here. In this particular instant in time, as the mode shape is pulling down the ends, the flange pulls itself apart. And we don't have it shown here, but if you move forward 180 degrees in phase, these ends will move up and this region will slap together. And so that's a nonlinear response. And so you wind up seeing these periodic impacts in that first bending mode when you get it moving pretty strongly. And then the stuck region, what we're calling the no-slip region, is right here, really close to the bolt, as we showed you with the contact measurements. Now, this next mode type is completely different. We wind up with torsional behavior, where one side of the plate is moving up while the other one's moving down, vice versa on the other side. And what happens to the joint is you start torquing it, and you wind up with in-place shear, or in-plane shear, I should say. And so here you wind up with a stick-slip region. So depending on how you are or where you are in the motion, you might find a moment in time where this region is entirely stuck together. And then as you move forward and there's a lot of motion, it'll start torquing and shearing and then slipping. And that's a very different behavior from the slapping behavior up here. And you wind up with very different damping behavior in these 2 kinds of mode shapes. And there's higher order modes that show similar behavior as well. So we looked at various ways of modeling those kinds of joints, and you can do them using those crazy detailed nonlinear models I showed you a couple of slides ago, but that is very painful and not something you want to do. And so Trevor went through and evaluated several different simplified linearized ways of modeling the joints, in particular the bolt spring constants. And you wind up with springs for the bolt itself, and then you wind up with another spring along that contact annulus as well. And there's different ways of modeling those, and I'm not going to go into the details, but Trevor tried a whole bunch of them and arrived at one that he liked the best. And if you're interested, you can look for the thesis. If you go to the CAV website, we have a link to student theses, and if you just plug in Jerome, it'll pull up a link to his thesis you can download and have a look at all of the different models that go behind these curves. But the way they were evaluated is you put the experimental frequency on one axis, we chose the X, and then his model frequency on the other, we chose the Y. And then if you have perfect agreement, then you wind up with a line that essentially just runs down the diagonal of this plot. Of course, nothing's perfect, but some models work better than others. And again, have a look at the thesis for the model that worked best for Trevor. A big challenge that he never did come through was looking at how the damping varied with vibration amplitude. as well as the preloading that you apply to the bolts. So I think I mentioned that it's quite common to torque up your bolts to about 2/3 yield, but not everybody does that. So Trevor went through and looked at 3 torques: low torque, medium torque, and high torque, and he defines that in the thesis. And we also looked at 2 different flange thicknesses. So we made the plates, started off with a 1/2-inch thick flange, bolted them together. Trevor did a bunch of measurements. Then we took them apart, machined down the flange to a 1/4 inch, and repeated. And there's a lot of data in here. The 1/2-inch flange data is up in here. You wind up with a higher frequency, which isn't surprising for a thicker flange. And then the thinner flange is down here, but we wind up with this kind of separated region here. The brown ones are for high and medium torque, and then the red is for a low torque. And so we wind up with this. It's not a huge drop. This is a pretty tight frequency range down here, but still, maybe about a 3 hertz drop in resonance frequencies when we went to a lower torque. And also we wind up with these loss factors. These are curves because what he did is he hit them and then let the vibration ring down. And so you wind up with the loss factor changing a little bit as a function of how strongly the vibration is occurring. So strong vibration gives you one loss factor, light vibration another. And the thesis is full of stuff like this. And I will give you one thing that he discovered is that the variability that we see in the damping is less than the variability we get when we take the things apart, put them back together, and repeat the measurements. So there's just uncertainty and variability that you get just by different instances of bolting the structures together. So there's still a lot to learn and figure out in this particular area. Our next highlight is from Steve Wells, graduated around the same time Trevor did. And we thank Carrier for sponsoring his research on large chiller noise and vibration. And when we first started this work, we had originally kind of laid out all this travel that Steve would have to do to go back and forth between various Carrier sites and Penn State. And I was actually talking to a colleague of mine at Penn State, recently retired, Damian Rose, who works in a physical plant. And I was telling him what was going on. And he said, we've got tons of Carrier chillers out at our West chiller plant. And sure enough, we did. So we went and talked to the chiller plant folks, and they were extremely gracious and said, absolutely, you can put a bunch of sensors on one of our chillers. In fact, here is the workhorse chiller that's on all the time. And sensor that one up and do all the measurements you want on it. So this is, in fact, at the Penn State West plant. And we are looking at a whole bunch of accelerometers mounted to the condenser shell that's down here, as well as the discharge pipe that comes out of the compressor, which sits on top of the chiller itself. There's another big tank behind this, but this wound up being the one that does most of the radiation and vibration along with this discharge pipe. There's also in the picture a traverse that we mounted some microphones to. And so we're continually making measurements of the vibration and 3 key microphone locations throughout months and months and months of operation time. And I'll show you that led to our future challenge in the very last slide. And that's the vibration and noise changes quite a bit depending on the load that's being put in the chiller, the exterior temperature and relative humidity, whether the outer chillers are on or not. These things are always running off design, and that kind of leads to a lot of variability in the vibration and sound. The noise comes from here. This is this is an internal impeller inside the compressor. And you get broadband noise, but most of the noise comes from these vanes that are rotating through, and you wind up with vane passing frequency tones. This particular impeller is split. So up on the top, we have a certain number of vanes, 11 of them. And then about halfway through the passage, the inlet is here. And then centrifugally gets propelled outward radially here. But about halfway through the passage, you wind up with splitter vanes. So the discharge, you have actually 22 of them. And so that means you wind up with very different flow going through the different passageways, depending on whether you're going through one side of the splitter vane or another. Early on in the project, we were visited by our friends at Polytech, and they were marketing something called the acoustic camera. And we talked to them during their visit and said, hey, do you mind running out to the chiller plant and aiming this camera at one of our chillers? They said, absolutely. And with Steve, they went out and kind of aimed all around and focused in on one hotspot which wound up being the bottom part of the discharge pipe. And we saw extremely strong 2 times vane passing frequency tones coming off of that pipe. So it was just a smoking gun of where to look. It's not where all the noise comes from, but it is a dominant source. And what we found is that the frequency ranges of interest here were just full of discrete, lightly damped resonances. There are resonances throughout the discharge pipe, but we're showing you here measurements that Steve made on the bottom part of the pipe, which is where the camera kind of pointed us to. And he made a bunch of plots like these. And you'll see them throughout his thesis. Once again, if you go to the CAV website and punch in Wells or Chiller or something like that, you should be able to find the thesis. But the plots all look like this. We have structural mobility over here on the left, and that's in black. So we see the resonances nice and cleanly, and he's put some mode shapes right above some of the key ones here. The numbers correspond to the mode order. So this is 1 half wave along the length of the bottom part of the elbow. And then 4 means 4 waves around the circumference. So an n equal 4 pattern. Here's n equal 5, here's n equal 6. And if you keep going, you get to 7, 8, 9, 10, etc. On the bottom in yellow is a surface to acoustic intensity transfer function. And so this is essentially taking the intensities measured in the microphones and then ratioing those to the vibration, surface average vibration of the pipe itself. And so you, not surprisingly, wind up seeing these strong peaks showing up at these particular resonances. So why is this important? Well, it's important because if that vane passing frequency happens to line up with one of these resonances, you're going to see a big amplification of vibration and radiated sound. And this gets back to that off-design issue. The chiller is constantly adjusting itself to meet the demands being placed upon it. And there's a controller in there that will adjust various things. And one of those things is how fast that impeller spins. And so if that impeller spins at a certain rate, that winds up giving the vane passing frequency a frequency that aligns with its resonance, that's high vibration sound. Broadband noise does come off the condenser shell, and it is dominated by a hump in response that corresponds to the ring frequency of the shell itself. And the ring frequency is just computed by looking at the overall circumference and the speed of sound in the steel. And incidentally, I did a separate talk about ring frequencies and some of the infinite shell and plate curves you're seeing on here, which I won't go into now, at last year's CV workshop. And those presentations should still be available online. If they're not, you can't find them, let me know and I can point you to them. Once again, we've got the structural mobility, and it looks kind of flat. It ramps up a little bit here. Looks a bit like a beam at low frequencies, and eventually it looks like a shell at others. But at a pretty low frequency, the shell curvature just becomes small with respect to a wavelength, a bending wavelength, and it looks just like an infinite flat plate. The purple curve is a more interesting one. That is, once again, the acoustic transfer function, so intensity divided by surface vibration. Embedded in that is the radiation efficiency of this shell. And now you can see this clear ramp up to a big hump where the shell radiates extremely well between about 1 kilohertz and maybe about 2 or 3 kilohertz, maybe 2.5. So that's kind of a sweet spot for the condenser shell radiation. So if you get a tone in there, it'll be amplified. But also we see some broadband noise coming out of the compressor that gets amplified by here as well. Oops. Now, what Steve did is go through and put together a hybrid approach to modeling and predicting the sound coming off of this chiller. And it had to be hybrid because there was no way to do this from first principles numerically. He's got finite element models of the discharge pipe because it's conducive to that. You really just have a few modes in there, and it's not that hard to model those modes. The condenser shell, the modal density is just extremely high. All these peaks in here are different modes. It's such a big structure and such a thin-walled structure that attempting to model something like this, the finite element model, would be just exorbitantly expensive. He actually did it and maybe got up to 1 kilohertz or so before the model broke down. It was just too coarse. And so what we're using for that model is statistical energy analysis. It's ideal for cases where you have a high modal density, high modal overlap. And so this is coupling together an FE model of the pipes and an SEA model of the condenser shell. There's some other pieces that are just too tricky to model from first principles or even SEA. And so those we wound up using measurements for. In particular, some of the radiated sound transfer functions you saw a minute ago, those are all based on testing. Steve going out there with his trusty hammer, measuring vibration, measuring microphone behavior, and then coming up with radiated sound transfer functions. And what he's allowing the customer, in this case carrier, to do here is go through and use scaling methodologies to kind of shift around the FEA results, the SEA results, the test results. What if the thickness of the condenser shell was twice as thick, or we changed the material, or something like that? What would happen to the overall response? What if we damped a certain structure more than another one? So here's a bunch of loss factors that were all measured throughout the course of the research. So there's a lot here, and I'm not doing it justice, but I'm just pointing out we're putting together a lot of different models and measurements to get this right. One of the big things he had to do was back out the forcing functions, because we did not have a first principles way of doing that either. And we were, however, able to combine a bunch of transfer function measurements and operational vibration measurements at the interface between the compressor and the discharge pipe itself. And they were able to back out what the structure-borne and the fluid-borne forcing functions had to have been to give us the observed vibration. And he was able to prove that by going through and comparing simulations, pseudo-simulations, again, it's a big hybrid model, to what was actually measured, and did that for several different cases. And so up here, we've got the discharge pipe vibrations, and the measurements are in these kind of light dashed red curves here. And the blue is a model output. And then we put plus or minus about 3 dB on the measurements for variability. Nice agreement, not perfect, but pretty doggone good, considering how complicated the system is. Down at the bottom, we've got the condenser structure. Once again, measurements with a spread. And then in green is the pseudo simulations. The peak you're seeing here at around 3 kilohertz, this is in 1/6 octabands. That is the fundamental tone coming out of the compressor. It's actually a 22 times shaft rate tone. And this is the one that's kind of moving back and forth between the resonances of the discharge pipe. And then finally, we've got radiated sound down here. And once again, a nice agreement between the measurements and simulation. Bit of a difference up at higher frequencies. Pardon my dog. It's the fun of doing live presentations here. But a very nice agreement here. And if you go to the thesis, you'll find a bunch of cool what-if studies, or what if you change this, what if you change that. Just as with the last one, I had a future challenge that was on damping. Here, the future challenge is on off-design assessments. So here, all the data points that Steve collected between June and October. Looks like it took a break in August. And each of these little symbols corresponds to a different flow head ratio. And so this is looking at the fraction of the flow as a function of on-design flow rate. So on-design flow would be right up here at 1. So you come up here. And then head fraction up here, completely on-design head would be up here. We don't actually have any points up there, which is kind of interesting. This green line is purely on design. So I guess the head fraction is maybe a little bit off there, but this would be where your blades of the compressor are aligned perfectly with the inflow, so you got optimal efficiency. And you're not at that point very often. Right? In fact, quite often you're under it. You're putting out less head for a higher flow rate. So this is the off design point. The reason you're typically under it is going over, you might surge, and that's a bad thing for compressors. And so this is a quite common distribution of operational points. So we've got vibration and sound data at every one of these points. Really not a whole lot of it looked at, just not enough time. Steve was fortunate enough to come through getting the on-design part right. And so we're having conversations with Carrier now about what we can do with this, looking at how bad the vibration and radiation can get. What are the worst case conditions? Can you avoid them? Can you use artificial intelligence and machine learning to perhaps look at where the worst cases are? That's a shameless plug for our Wednesday CAV meeting on AI and machine learning in vibration and sound. One more update, and actually there's a short one at the end of all this, and this is work done by Gage Walters advised by Andy Wixom and Sherry Martinelli. It's also sponsored by NAVC. Gage actually did not go to work for NAVC, went to work for Johns Hopkins, but still a good place to land. And his big research project was looking at uncertainty quantification. This is always something we get asked by our sponsors. You're giving us predictions. How uncertain are the predictions? And we've never had a great way to answer that question. And Gage went through and did a nice job in helping us get there. So let's show you an example. And this is looking at a plate that is excited by turbulent boundary layer flow. And the plate that he looked at was something that a fellow named Maestrello examined way back in the 60s and 70s. Well understood plate, pretty high speed flow, a Mach number of about a third. And some of the stuff you're seeing down here are parameters associated with the boundary layer itself that you need to capture the forcing function appropriately. There's plenty of empirical models for boundary layer forcing functions, and these parameters get fed into those. And the mission here was to look at first vibration and then radiated sound. Maestrello put these plates in a wind tunnel, but put an anechoic chamber right below the plate so we can measure the radiated sound fairly accurately. So how do you handle uncertainty? I mean, all of those boundary layer parameters I mentioned a minute ago, they're highly uncertain. I said empirical models, they're very empirical. We really don't know for sure how to model a boundary layer induced forcing function. You can try it with like really advanced CFD methods, but that's awful tough. Hence using empirical models. But all of the empiricism, it's highly uncertain. How fast are the turbulence eddies flowing inside that boundary layer? That's kind of up in the air. How correlated are they over space? Again, there's models that are fit to measurements, but there's a ton of scatter in them. The boundary conditions on the plate itself, you bolt this thing down and that's uncertainty. That leads to uncertainty in damping. The material properties are uncertain. So I've rattled off like maybe 5 or 6 uncertain variables right away. And typically the way you would do this in the old days was using something called a Monte Carlo method. And all that means is randomization, right? So you take all your uncertain variables, decide what ranges they have. So maybe the damping in the plate ranges from 0.05 to 0.15. And you assign a variability to that. Is it a uniform variability and a normal distribution, something else? And you have to do that too. And then you just essentially generate this insane number of possibilities over that space, over all the variables you decide are uncertain. Turn on the simulator and come back in a week or a month and then look at your results. The good news is there's much smarter methods that have been developed since then. And one of them, which we're using here, is called Generalized Polynomial Chaos. I love that chaos at the end, GPC for short. And what this allows you to do is essentially represent or approximate a true Monte Carlo rigorous simulation with a bunch of polynomials and a few points to define each polynomial. So you're reducing the number of evaluations you have to do by orders of magnitude. That's the beauty of this. Now, there's more work to it than just that, especially with multiple variables. And in Gage's thesis, you can find all the details. This is an attempt at looking at a 4-dimensional space. I'm not even going to try to explain it. They explained it to me once, and I got lost. But this is 4D space. The point is that we're representing a 4-dimensional space. There's 4 variables you've decided are uncertain, with only 137 points, 7th-degree polynomials throughout, and getting the answer. So that's the beauty of this. And there's a bunch of validation stuff you'll find in the thesis to confirm this works, but I'm not going to focus on that. I want to show you what happens at the very end, which is what I think is the coolest part. This is what the sponsors are asking for, right? Give me your prediction and give us a variability. So here's the experimental data in symbols, no variability about that. But this is all 1/3 octave, but the simulation is in the middle, and then here is in fact the uncertainty with 95% confidence. Over here on the right is in fact the uncertainty distribution. 0 is your mean prediction. And then the way uncertainty works is you compute a standard deviation. Twice that is a 95% confidence, 3 times is 99%. You can go up and beyond that, right? And then the orange is in fact the possibility region. This is the actual range of possible outcomes. What, interestingly enough, is actually inside the 99% estimate. That's statistics, right? It's the way it can be sometimes. But you wind up with spreads where it gets a little bit higher variability, usually near resonances. Right here's the first resonance. And then maybe less variability at others. But this is the kind of thing that you want to know. What's my variability with what confidence, right? So here it's 3 or 2.5 dB-ish for 95% confidence. Now, here's the cool part. What uncertain variables are responsible for this variation? And Gage looked at a bunch, but I'm showing you the two that matter most. So this is looking at radiated sound power. Now we're in narrowband space because it's just more interesting to look at. Once again, you got the prediction and the variability. And there were 4 variables he looked at, and these are the ones that matter most. The one on the top that says alpha, that is associated with the forcing function. And in particular, this is how correlated the turbulent excitation of the wall is in the streamwise direction, the flow direction. And there's 2 curves on here. The orange is the total variability, and the blue is alpha's contribution to that. So you can see that the flow-induced variable uncertainty gives you a broad band variability in your output. Looks like about 1.5 to 2 dB pretty much across the board. On the bottom is uncertainty in the Young's modulus of the plate. And this looks completely different. So once again, orange is total, and then blue is the contribution of the Young's modulus. And this is solely around the resonance frequencies. Why? Because if E varies, the resonance frequency varies. So the variability is actually shifting back and forth just a little bit. And that causes these big spikes in the variability as your resonance dodges around. So structural parameters like E, perhaps mass density, are going to give you this kind of strong variability around resonance and uncertainty in your flow-induced forcing functions. And we could have put convection velocity on here too, give you a more broadband variability. Okay, one final one, and this is a single slide. Cameron McCormick is about to graduate if he hasn't already. And I mentioned before that we did a short course on acoustic black holes last year. And Micah Shepard's, one of his major research foci, is on optimization. And in fact, his thesis was on that. And so he turned Cameron loose on optimizing the acoustic black hole configuration. So we just have a few of these, and this is just the last slide. And some of you may have remembered seeing stuff like this from some of our international guests that are also looking at black holes, but there's different ways of doing it. First, what the heck's a black hole, right? This is just a zoom of an indentation in a plate. And imagine you've got a bending wave coming along here, and all of a sudden it encounters this drop in thickness. That looks like an impedance change, so you're going to get some reflection off of that. But the other thing it's going to do is that as the thickness decreases, the bending wave slows down. So all of a sudden, where you might have had just a few wavelengths along a pretty long distance in the main plate, you've got a whole bunch of wavelengths, and the wavelengths continuously vary as you work your way down to the middle here where the thickness is smallest. So you get really tiny wavelengths there. And then if you let it go, the waves would continue on and come out the other side. Sometimes they'll get trapped, and so maybe the vibration is less over here just because the impedance drop in discontinuity. But the black is what really helps you with acoustic black holes. It damps out the vibration when it's at its smallest possible wavelength. There's other stuff they can do too in radiation, but the focus here is on vibration. So there's different ways of doing the black hole. Here's one, the simplest way. You drop down the thickness, add damping. Here, you're just dropping the the thickness on one side and not both. And so instead of having vibration in your center line, it's down here at the bottom. Once again, black as a damping treatment. And then here's another way of doing it. You can hollow out the inside. That's a little bit harder to do manufacturing-wise, but with additive manufacturing, all things are possible, right? Once again, damping over here. And so these shapes are what we're optimized, right? So if you look at the black hole literature, it's all pretty much on what the shape ought to look like. And then where you put your damping was added in this study. And here are some papers that Cameron and Micah did. In all of these plots you're seeing on the right, the dashed lines are the baseline, and then the colored correspond to the particular case that we're looking at here. So dropping down the black hole and going to a small thickness in the center, buys you a little bit, maybe at high frequencies. I'm going to drop down to the bottom here, carving it out in the center, maybe a little bit better. right? You're kind of moving the vibrations out of the outside where your damping material is. Maybe it does a better job of treating it. You can see the damping is clearly higher for the orange than it is for the purple. But the winner is this huge divot and then the damping material adjacent to it. And here you can clearly see strong vibration reductions due to damping, and the fact that you've kind of tailored the damping in the region where it does its best possible job. And this is actually probably the best for manufacturing. You can kind of take a piece of sheet metal and maybe pound this out and then slap some damping on the other side and off you go. All right, so that is it for my overview. And please leave comments, leave questions in the YouTube chat or whatever they call it. And what we'll do is maybe grab some of the questions you've got. And when we have our live session at 3 o'clock Eastern Time on Monday, October 26th, we can go over some of the questions that you guys have. Thank you very much.